here's another problem where we're given an iterated integral that's already set up for us. These limits of integration don't look too great, although they follow a pattern that we're going to want to recognize. So some of you may recognize what region we're working with here. If not, you're going to want to pay special attention when we're figuring out what our region is. What I want to do first, though, is focus on the fact that the integrand is 1. Because when the integrand is 1, if these limits of integration are describing a nice region, I might be able to evaluate the integral by using geometry rather than calculus. So I'm going to start with an example of just a single integral. If I just had a single integral, but my integrand was 1, I could certainly do this algebraically. I could find myself an antiderivative of the constant function 1. But I prefer to think of this more geometrically. I've got the interval from A to B on the x-axis. I've just picked random points to put there. Okay. But then the height that I'm integrating is a constant height of 1. So that's determining a horizontal line, and I'm looking for the signed area that lies between that line and the x-axis over this interval. Well, that's going to just be this area of this rectangle. But I know that the area of a rectangle is just base times height. The base would be b minus a. The height would be 1. I'm going to get b minus a, which you'll notice numerically is the length of the interval. Now, I said it's numerically the length of the interval, because if I were calculating that as an area, the units for this would be square units. If I'm calculating the length of the interval, it would just be plain old regular units. But the number would be the same. If the distance between A and B was 5, I would be getting 5. Okay? So the numerical value that I get is the same number I would get if I was measuring the length of the interval, although technically the units for the integral would be different than the units for the length. Okay. So we'll have something similar if I have a double integral with 1 as my integrand. I can think of that geometrically as well. So if I have the region D and my integrand is 1 and I'm integrating that dA, okay, well, D is going to be some sort of a region in the xy plane. I don't know exactly what it looks like. But what I'm doing then is I'm attaching a constant height of 1 to every single point in that region. And if I attach a constant height of 1 to every point in that region, I'm going to get a shape that looks something like that. Not too bad. Okay, but what I'm going to be getting is I'm calculating a signed volume because my height is positive. I'm actually getting a volume, but I'm getting something where I'm going to simply get the area of the base, which is D, times that constant height of 1. So if I'm integrating 1, I'm simply getting the area of the region D, and I can think of that geometrically. Now, there may be times when the region D is a blobular region like I drew here, so there's no geometric formula for figuring out what that is, and I would actually do the integration to calculate the area. But there may be other times where my region is actually a nice geometric area. So if I wanted to evaluate this, I have two options. It's set up as an iterated integral, so I could go ahead and do the iterated integral if I wanted to. I'm just not crazy about those limits of integration, so I'm going to explore a little bit and see what this shape is. So I can see my x values are varying between -1 and 1. So my left and right boundaries are at -1 and 1. The bottom boundary is y equals -√1 minus x squared. That's the bottom. And the top boundary is y equals positive root 1 minus x squared. Now, when you see things where you've got a square root of a subtraction problem and a variable squared, pay attention. To see what this looks like, I'm going to square both sides. So I'd say y squared is equal to 1 minus x squared. But in squaring both sides, I just lost some information. Because here, I could see that this y value was never positive, because it was the opposite of a square root. Here, it looks like y could be positive or negative, so I'm going to just make sure that I record, I want just y less than or equal to 0. But if I add over that x squared plus y squared equals 1, y less than or equal to 0, I know what that looks like. That's the unit circle. This says take the bottom half of it. Very similarly, if I square both sides here, I get y squared equals 1 minus x squared, except this time I want y to be bigger than or equal to 0, because this expression is never negative. But that's x squared plus y squared equals 1, y bigger than or equal to 0. That's the top half of the unit circle. So this is the region that's described by these limits of integration. It's just the unit disk. Okay. So I could say this is the double integral over d of 1 dA, where d is the unit disk. But we just saw that means I'm taking the area of that disk, I'm attaching a constant height of 1 to it, so the volume that I'm going to get is the area of that disk. It's the unit disk. It's pi times the radius squared. Okay. And the radius, of course, is just 1. So that integral would be pi. So that's a very nice thing to be aware of. And I am totally fine if you're given something like this where your integrand is 1 and you recognize the region over which you're working. I'm totally fine with you calculating that by doing pi r squared rather than doing the integral. And it's actually much simpler if you recognize that.